research interests focus on using modern analog systems, including terrestrial hot springs, which I think he'll talk about today, as well as some of these other locations to explore geochemical mysteries, the Archean and Proterozoic. So Jeff approaches analysis of modern systems through a holistic lens, characterize geochemical environments as context for disentangling microbe water-rock interactions. All right. So Jeff, with that said, I will give you the screen.
Great, thank you. Great. So, oops.
And while we're waiting for Jeff to get ready, just a reminder that we will do questions at the end. So just please, write down any questions you may have, or just make a mental note, and then we'll get to that after Jeff's talk. Okay.
All right, great. Well, thanks so much, everyone, for inviting me and allowing me to talk to you a bit about hot springs and their connections, I think, to origins of life. And so, without further ado, let's go ahead and get started. So my goals for this talk are to introduce myself and my research and provide an overview on drivers of hot spring geochemistry. Oops, I forgot to turn my pointer into a laser pointer. There we go. Provide an interview on drivers of hot spring geochemistry and make connections between hot spring geochemical environments and the origins of life. So those are the goals I have in mind with this talk today. So to start off with the introduction myself. So my science looks like a holistic approach. So I like to characterize the geochemical environments that I study as much as possible to maximize the impact of our work and to make it as useful as possible for others. And so this means I end up needing to use a lot of different types of instruments to analyze precipitates, sediments, rocks, biofilms, water. And so in terms of like major anions, ion chromatography, major cations, trace elements, IC, ICP, AS, ICP, MS, and on to imaging and elemental mapping, quantification methods, and then lots of stable isotope methods as well, just to give you an idea of the types of techniques that I often use. And so because of kind of the wide spectrum of the things I'm interested in, my science gets a little tricky to categorize. So there we go. Wouldn't advance there for me. Sorry about that. So things I work in can fall into a wide range of different categories. And so what this ends up meaning is that I love collaboration. So my background is chemistry, moving into earth science and geochemistry. I work with a lot of different people so that I can bring my expertise towards them, and then they can bring their expertise to me, and then through that collaboration, we can do fun and exciting science. And so very important to acknowledge some of my collaborators that I've worked with, including for stuff I've talked about with this talk in particular, but I just a cornucopia of wonderful, awesome people that I've had the great fortune to work with and continue to work with moving forward with a lot of my different projects. So just a shout out to them and thanks to them for being awesome and dealing with me. And so for me, my science involves a lot of field work. For me, it's very important to get out to the outcrop as much as possible to see and poke at what I'm studying. And so this has gotten me out to glaciers and periglacial terrains, gotten me out to lots of different geologic outcrops, lots of different hydrothermal systems, et cetera. And so for me, it's been very transformative and very helpful in my understanding. Now, next, I want to provide an overview on the drivers of hot spring geochemistry. So this will be a primer based on everything I've learned, and to get you, hopefully get you all up to speed. And so if anyone needs any clarification on anything, please let me know. Otherwise, I'll just kind of charge ahead. So oftentimes when you think of hot springs, especially in terms of Yellowstone, there's usually two things that crop up. Usually the two famous, one being Grand Prismatic Spring on the left, and Old Faithful, the geyser in the Upper Geyser Basin on the right. And but want to caution, and I think this is something that kind of oftentimes cloud people's perceptions of hot springs and hydrothermal systems in general, is that those are far from the whole story. Those are just happen to be cool, popular things that a lot of people see. So before we get into it, quick timeout on what I'll be talking about and some terms I might use. So like major anions would be, for example, chloride, sulfate, fluoride, bromide. Major cations would be sodium, potassium, calcium, magnesium. Trace elements is a cornucopia of elements that for us typically, include lithium, potassium, iron, barium, et cetera, et cetera. And then dissolved inorganic nitrogen is it involves either ammonia, nitrite or nitrate. And then dissolved carbon falls usually into two categories. One is dissolved inorganic carbon, which can include dissolved CO2, bicarbonate or carbonate anions, and then dissolved organic carbon, which is effectively just anything that's organic and in the water. And we filter through a 0.2 micron filter for any of our water samples. And so when we say something's dissolved, that means it's smaller than 0.2 microns. So that should eliminate all cellular material. And to be a little more specific about things I'll be touching on today, so chloride and sulfate will be prominent in this talk. And then total dissolved inorganic nitrogen will be a term I use. So that's a sum of those different inorganic nitrogen species. We'll talk about magnesium, a slew of trace elements. And with dissolved carbon, I'll talk about dissolved inorganic carbon, which is the combined fraction of dissolved CO2, bicarbonate, carbonate, anions, and then dissolved organic carbon is DOC. So you'll see those terms. So, the reality of a hydrothermal system is there's a lot of different things. So, of course, grand prismatic, but we have eruptive, pulsing, circumneutral to alkaline springs. We have continuously flowing springs that can have chemotrophic to phototrophic microbial communities in them. You can have mildly acidic to circumneutral hot springs, where you can have silica precipitation occurring around them, and they can look a fair bit like the alkaline systems, but they are different. And we even have places where we have stromatolite reefs growing, and microbial mats growing right up next to gas sources. And then we have acidic sites such as mud pots and seeps where we have high sulfide precipitating sulfur, and fumaroles, of course, as well. And so, what drives these surface expressions, and why do we get these at the places we see? So it all comes down to subsurface processes, and this is near subsurface. So within the top 100 meters or so of the ground surface, typically, and sometimes even closer than that. And so I'm going to just walk you through this cartoon really quick to inform you on what I'm talking about. So at Yellowstone in general, we have this idealized model of precipitation falls in the surrounding highlands. It moves the subsurface groundwater transports to a place where it can intersect with brines being released from the magmatic chamber. And then as those rise, mix with that subsurface water, you have your deep hydrothermal source that then rises to the surface. And then that's where things can get really interesting. And so to the left is the minimum subsurface boiling, so minimum phase separation. These are your circumneutral to alkaline hot springs. So your Old Faithfuls, your Grand Prismatic Springs fall under this. And so this is where you have the deep surface coming up, there's minimal subsurface boiling. And so you just basically have the deep source coming up, interacting with groundwater and reaching the surface with minimal processing. Now, in other locations, we have phase separation. And so this is where we can get some really interesting, exciting, and different expressions. So here we have subsurface boiling happens. So the heat, the heat of the rising water outpaces the overburden, keeping the pressure high. And so it can flash boil in subsurface. When that flash boiling happens, just like your pot on your stove, you get two phases. You have the part that's still in the pot, the liquid phase that's boiling, and then you have the vapor or steam that's generated, and that's the vapor phase. And when that happens, chloride and sulfate anions, which were in the original deep source, they partition and stay in the liquid phase, that residual liquid phase. Whereas gases such as hydrogen sulfide, those get stripped out and move to the vapor phase and get concentrated there. And then that vapor phase will cool and condense. And so you end up with these two primary end member water sources. And of course, these can interact with groundwater, which has oxygen in it as well. So you can get dilution and oxidation happening. And that's especially important with this vapor phase, where to just remind everyone that hydrogen sulfide reacts with oxygen to form sulfuric acid. So that's a critical component for what I'm going to talk about. And so with this oxidation and generation, that's where most of our acid comes from when you think of really acidic systems and low pH. It's sulfuric acid. And so as surface expressions, you can get hot springs that are predominantly fed from that liquid phase, that residual liquid phase, and those will typically be mildly acidic to circumneutral. And then you could have the other end member where it's vapor phase, where there's a lot of sulfate as sulfuric acid. You can still have a lot of sulfide, and your pH can be 3.5 to 2 to 0 even, especially for fumaroles. But also it's always messy in the subsurface in these systems. And so you can get mixing where you can have some amount of residual liquid phase, some amount of that vapor phase. And so these are really, really interesting sites where you can have intermediate pHs. The chemistry can vary wildly depending on the subsurface plumbing and how much they're getting from the vapor versus liquid phase. And these can undergo quite a bit of change if the plumbing changes in any way due to earthquakes or precipitation or dissolution of the conduits. And so that's kind of the framework for thinking. But then what I want to do is transition to thinking about this in terms of geochemistry. And so just as a quick reference, we're going to be talking about water that has been collected from a wide range of hydrothermal systems. So here, this is the map of Yellowstone National Park. And then we have the most recent caldera forming eruption caldera outlined here. And all of these hot springs fall close to or within the overall caldera system. So the largest caldera actually is north of here a bit. And so all of these are either right on the border or within the entire caldera complex. And just to give you an idea of where all of these hot spring samples we're going to be talking about come from. And so just to really make sure everyone's clear on this, so we have chloride is the conservative tracer of the deep source. So chloride, we're not adding or subtracting that; it is just staying with the liquid source and the liquid phase. Sulfate is a dynamic tracer, so you have some sulfate coming up with a deep source, but you also have some sulfate being produced from oxidation of hydrogen sulfide. And so if we plot sulfate versus chloride, it actually allows us to do a pretty good job of teasing apart those three different sources for hot springs. And so that's what we'll be getting into. So this plot on the right, we have chloride plotted on the x-axis in logarithmic scale. And then we have sulfate plotted on the y-axis, also in logarithmic scale in millimole per liter concentration. And I'm going to kind of walk you through the different phases here. And the key just shows where these different hot spring systems were sampled. But what I want to show you, so minimum phase separation, so where you have very little or minimal subsurface boiling, this is where all of those types of samples pile right there in that region. So all of your Grand Prismatics, Old Faithfuls, and Lower Geyser Basin, Upper Geyser Basin types of hot springs, which many people think of as typical, they all fall in this tight little cluster. When you get the phase separation, the liquid phase drives to increasing chloride and slightly increasing sulfate just with concentration from loss of steam, loss of water. And so the residual liquid phase drives into this direction to the right, whereas the vapor phase dominant, you don't have any chloride, but you have high sulfate concentrations from that sulfide that's oxidized. And so we have our end members of vapor phase dominant, upper left, high sulfate, very low chloride. The residual liquid phase down to the right, where you have higher chloride and higher sulfate than the source water. And then we have remixing potential. So where you could have some vapor phase or some liquid phase or some combination thereof, all in this field in between. And so this is the framework that we use to tease apart the sources for hot springs in Yellowstone National Park. And this represents about 700 individual samples from a slew of hot springs across Yellowstone National Park based on a map I showed you. So that's a lot. So hopefully that makes sense for everybody. So then once we have this framework to work with, we keep in this chloride versus sulfate space, this allows us then to look at other parameters. For example, here I have plotted pH and binned them in terms of acidic, so 3.5 or less, or 3.5 to 6.5 is intermediate, and then circumneutral to alkaline is 6.5 and greater. And so plotting this in the chloride versus sulfate space, we can see where the acidic systems, unsurprisingly, are the places where we have a lot of vapor phase dominance, either vapor phase dominant or predominant, and so that drives the pH low. With the intermediates tend to be in this primarily residual liquid phase with some vapor phase input, and then the deep source tends to be circumneutral to alkaline, and some of those residual liquid phase ones also fall in that same category. So allows us to then, with pH, of course, pH is hugely important for dissolution and solubility of a lot of trace elements, for example. And so this is the power of being able to use this to see how the geochemical environment is driven by those subsurface processes. So now I want to take you thinking in this space along with some other elements. And so we have lithium, aluminum, arsenic, and gallium. And so these are elements that are essentially unimportant for life. So they're not critical for life. And just to give you an idea of how then using this chloride versus sulfate space allows us to see how things are what's happening. And so with lithium is sourced from the deep source. And so we get the highest concentrations of lithium associated with this residual liquid phase where you have concentration of the lithium, but this deep source is also relatively high. And subsequently the vapor phase dominant systems tend to be very low in lithium, and they're primarily picking it up just from dissolution of local rock. Whereas aluminum, you have high aluminum in the acidic sites, so dissolution of local rock and soil, relatively low aluminum in the alkaline springs, which is unsurprising when thinking about solubility of aluminum in high pH systems, and the same for residual. Gallium, we don't have as many data points, but gallium seems to follow with the deep source. And this is one that's interesting in terms of trying to follow what's happening with silica precipitation. And arsenic is present as an oxyanion primarily. And so it is relatively high in the deep source, gets concentrated with the boiling in the residual liquid phase. And so that's where we see the highest concentrations of arsenic. And then in the acidic systems, typically where we see arsenic as a cation. And so this is also interesting thinking in terms of how life deals with arsenic when they need phosphorus, because arsenic typically is an oxyanion arsenate, which mimics phosphate. So now I'm going to walk you through the more biologically important. So we'll start with carbon, nitrogen, and phosphorus, but here's a quick summary. So unreactive cations follow the deep source, right? Solubility versus local dissolution rock soil. So we see dissolution present from these high aluminum concentrations. Redox sensitive oxyanions, we can follow what happens with them. And then we can start to track what's happening with mineral precipitation solubility through gallium. So moving on to carbon, nitrogen, and phosphorus. So those terms I mentioned before: dissolved inorganic carbon, the upper left; dissolved organic carbon, upper right; total dissolved inorganic nitrogen in the lower left; and then total dissolved phosphorus in the lower right. And with this, we have relatively high, and of course, all these plotted in that same chloride sulfate space. So the dissolved inorganic carbon is relatively high in the source. So that's the carbon source from the volcanic source dissolved in the water. And then with boiling, that strips out a lot of that carbon as CO2. And so we have relatively low concentrations in the residual liquid phase and very low in the acidic phases. Dissolved organic carbon is highest in the acidic sites, and this follows with that dissolution of local rock. And so this is typical of stuff being transported into these acidic systems from the local area. So bison like to congregate in these areas. And so that can be a source of organic carbon from bison poop. Whereas organic carbon tends to be relatively low in the deep source. To total dissolved inorganic nitrogen, the story is most of it typically is phosphor, or is nitrate coming in with the deep source water. So that's typically brought in with groundwater. It can be elevated a bit in the residual liquid phase, but it's highest in the vapor phase, and that's because any inorganic nitrogen that is in the water gets reduced and then volatilizes and stripped out with boiling as ammonia. And so ammonium gets concentrated in the vapor phase water. And so we get high concentrations of total dissolved inorganic nitrogen as ammonium in these acidic systems. So we have high nitrogen where you have vapor phase dominant systems. And then phosphorus is kind of a crapshoot. And really, there's no real trend. Most of it is probably coming in from surface sources. And it's typically relatively low, fairly low concentrations. And so when thinking in terms of phosphorus and DOC, where is that coming from? That's where we have to remember our context. So of course, all these hot springs are within the greater Yellowstone ecosystem with bison that spend time there during the winter because there's less snow present. And so they produce point sources of phosphorus and dissolved organic carbon, but of course also the greater ecosystem in general. And so we always have to remember when thinking about these things that we're in a modern system with this context. So really to get into the weeds, this is a lot. And so don't try to digest this too much. I'll just walk you through some highlights. So we're looking at magnesium, vanadium, manganese, iron, cobalt, nickel, copper, zinc, and molybdenum. So kind of a hit of the most important trace elements for life in terms of enzymatic processes, especially. And so what I want you to take home is that we can start to anticipate trends of where higher concentrations and lower concentrations of these elements would be for these different types of inputs for hydrothermal systems. And then we can also start to tease apart redox sensitivity and solubility impacts on different elements as well. And so, for example, manganese has some actual very high concentrations that are present in some of these remixing zones where you have intermediate pH. So there's some interesting things going on with manganese, for example. Molybdenum is present as an oxyanion, and so it comes from the deep source, is concentrated in that residual liquid phase, relatively low in the vapor phase. So that has implications for potential implications for nitrogen fixers who need molybdenum to build the nitrogenase enzyme that allows them to break that nitrogen triple bond to fix nitrogen. And then, of course, you can pick your trace element favorite and see how those also react and interact with these, and they're driven by these systems. And one in particular I want to point out is magnesium as a divalent cation, which is important for oxygenic photosynthesis. We have higher concentrations in the acidic sites where we have dissolution of local rock, relatively low in the deep source and residual liquid phase. So we actually have a depletion of these divalent cations. So keep a pin in that. So that's nice, and that's great for Yellowstone, but it's a bigger question is this important for all hydrothermal systems? And so, which is very valid, right? So Yellowstone is, for those of you who are unfamiliar, is hosted in a predominantly rhyolitic system. So lots of rhyolitic rock. And so does this way of doing things translate to other geologic settings? And the short answer is yes. And so this is some preliminary data in a manuscript I currently have in preparation, where we bring the large data set from Yellowstone together with large geochemical data set from colleagues that are working in New Zealand, specific the Tuapu volcanic zone, the TVZ in the North Island of New Zealand, and then a colleague working in Iceland. So these are hydrothermal systems across Iceland. And so we have a rhyolitic mid-continent hotspot, intermediate subduction zone, back basin spreading zone, and then a basaltic rift zone driven by mantle plume. And the short answer is that we see the same patterns emerging from all of these. And so shouldn't be surprising. Physics is physics. It works for all these systems. But then the slightly less short answer is that there are some differences due to those geologic settings. And so that's, stay tuned. More to come when we get that paper published. But generally we can make some inferences about the geochemistry of ancient hot springs, thinking in terms of the systematic approach, and thinking in terms of what that means for what elements could be available. So then, just as a real quick exercise, you don't have to dwell on this, but just to give you a flavor of it, right? So then we could predict that, like for a minimum phase separation hot spring in the Archean, we would expect relatively high input volume and relatively high outflow rates, circumneutral to alkaline pH, moderate to high concentrations of certain elements, low concentrations of others, and then a relatively low impact from dissolution of local rock and soil, high precipitation rates, and really relatively long-lived, persistent, stable geochemistry kind of system with these. And for a vapor phase dominant system like this pool or this sulfate precipitating seep, right? We expect a small input volume, low to no outflow, low pH, high concentrations of certain elements, low concentrations of others, high impact from dissolution and inputs from local rock and soil, and low silica precipitation rates. And then for a predominantly residual liquid phase fed system, hot spring, we'd expect small input volume, low outflow, mildly acidic to neutral pH, high concentrations in some elements, moderate to low concentrations of others, moderate to low impact from dissolution of local rock and soil, and low to moderate silica precipitation rates. And then round out the ones that are where you have mixed phase input. That's where small input volume, low to no flow, but and mildly acidic to neutral pH with maximum geochemical variability. Like these are wild and can change pH units over a year or so, or multiple pH units. And again, we can make predictions about what's high and what's low in terms of elemental compositions and what's in them. And these typically are relatively high impact from dissolution of local soil and rock, and relatively low silica precipitation rates too. So just kind of give you a flavor of what we're thinking in terms of how we would predict chemistry in a geochemical environment for the Archean based on what we're learning. And of course, with large data sets from multiple geological settings, we'll be able to do better. And ultimately, a goal for me is to do a better job of interpreting the rock record. So if we can find an outcrop with textural hints on as to what kind of hot spring is present, we could then predict what the geochemical environment was for the microorganisms that were present when the hot spring was living. So here's an example of a now extinct thermal system where there's a little geyser, a vent in the center, and then some geyserite around what was an old vent with colleagues, Professor Trinity Hamilton and Michaela Dobson, who wasn't able to give a talk today. So shout out to Michaela for letting me fill in for her. So that was a lot to digest. So hopefully everyone is keeping up, and I haven't completely gone into the weeds too much with this. But I wanted to then make some connections between hot spring geochemical environments and origins of life. So after setting up, giving hopefully a flavor of how we can use these data sets to think about hydrothermal systems and geochemical environments. So what does that mean in terms of origins of life and our thinking about origins of life? And so, what about hot spring environments and origins of life and early life development? And so I have some different areas here just to give you a flavor. And what I want hopefully what your eye is drawn to is that there's lots of hot springs close together. So here's West Thumb in Yellowstone National Park. Here's North Geyser Basin. These are all pictures taken from the boardwalk. So North Geyser Basin, looking at or the Porcelain Basin up here. Lots of different types of hot springs all packed together. This is the Firehole Lake area. Again, lots of different types of hot springs packed together. And the Upper Geyser Basin. Lots of different hot springs all packed together. So consistent across all hydrothermal areas is chaos rains. And this, consistent with Iceland, consistent with New Zealand, and any other hydrothermal system that I've ever seen, that there's a lot of different hydrothermal expressions, different hot springs that are relatively close together spatially, and you can have a lot of different types of geochemistry happening within close proximity. So you can change orders of magnitude pH over just a meter scale. And with these, you can get constant change at scales of seconds to decades, wide ranges of geochemical environments, close proximity, and lots of opportunities for mixing, including geysing, outflow intermixing, and outflow and hot springs flowing into each other. You can have splashing or bubble popping leading to aerosol generation, so transport to other hot springs that way. And so effectively, hydrothermal areas can bring billions, trillions of experiments and drive those every day. And so that's a super powerful tool to have a lot of different geochemical environments all interacting with each other and all in close proximity, right? So it's a very exciting way to, and very messy, fortunately, way to do some chemistry. So what are some benefits of hydrothermal systems? I'll kind of walk through just a few of these that have been highlighted by other authors. So one is wet-dry cycles. So this drives polymerization. So drying out and then re-wetting chemicals can drive the creation of longer chains. And this can happen in terms of geysing or eruptive cycles, like Old Faithful. You can have splashing from gas escape, like this example here, this little hot spring in the Upper Geyser Basin. So lots of splashing occurring, and then even diurnal cycles where you have what's called frying pans. So this is a frying pan in Iceland in the Landmannalaugar region. So in a frying pan, for example, it's predominantly vapor phase. And what happens is during the night, you get condensation and the pools fill up from the vapor phase coming up from the subsurface. And by the morning, they have water in them. But then through the heating of the day, you actually lose that pool of water faster than it can be refed. And so you actually have drying out. And so this is in the morning. By the end of the day, this is just a dry, almost like a fumarole, just a hissing dry pile of sediments. And so you can actually have that acidic systems where you have wet dry cycles as well. And of course, you can concentrate things in hot springs much easier than you can concentrate things if you're in the ocean. So that's a huge benefit as well. You don't have that dilution pressure from a large body of water. And this is from a really fun little experiment that we did with Dave Deemer and Bruce Damer and the grad student, where we looked at what happens with lipids in hydrothermal waters. Just literally, if you put in some lipids, what happens? Can you generate some protocells? And what we found was really fascinating. In hydrothermal systems, high pH, so here's a pH 8, here's a pH 3, and so it doesn't matter the pH. If you put in a wide range of different types of lipids, they form little vesicles. Whereas in simulated ocean water, they crystallize. And so if you have a high calcium water, you'll recognize that as soap scum or the brown layer that kind of forms in your bathtub. So these lipids if they're in presence of high concentration of divalent cations like calcium and magnesium, they precipitate as crystals. And so they crash out of solution, which of course makes it so you can't, really hard to try to make a cell. And this is due to that, if you remember that magnesium concentrations being relatively low, in these hydrothermal systems, what happens is you have precipitation of carbonates in the subsurface with that hot water before it reaches the surface. And so it effectively strips those divalent cations before they reach the surface. So that's a huge benefit, is allowing for lipids to not crystallize. Also, hot springs provide a ready redox gradient in terms of sulfur. So the mantle is at equilibrium with sulfur as sulfur dioxide. But then abiotic disproportionation and reduction processes can convert that sulfur dioxide into hydrogen sulfide and sulfuric acid, which means you have a reduced and oxidized form of sulfur being delivered, as well as sulfur dioxide being delivered as well as a gas. And so this provides a ready redox gradient that the microorganisms will have available to take advantage of for metabolisms. And it's just as a fun side note, the Curiosity rover has found both reduced and oxidized forms of sulfur in Gusev crater. So just evidence that Mars would have the same process. You still have a redox gradient being provided from the subsurface. And from some work we did on hot springs that we think represent potential early Earth analogs, we found that even modern systems can support a complex sulfur cycle, even in low biomass systems, and even anoxygenic photosynthesis. So for those that aren't familiar, oxygenic photosynthesis is what you see with plants and with cyanobacteria, algae. That's the green things. So when they do photosynthesis, they produce oxygen. So the oxygen. If you have and that requires photosystem 1, photosystem 2. But there's microorganisms that can use just photosystem 1 and take advantage of either iron 2 or sulfide or organic molecules to drive anoxygenated photosynthesis. And so we found those in some of our thermal systems where there's sulfide present. And so on the left, this is showing SEM images of balls of sulfur that were forming in a hot spring. And then these balls of sulfur have microbial communities that colonize them and oxidize them. So we have oxidation of sulfur. And in that same system, again, here's EPS, so microbial community, there's also reducing that sulfur to sulfide and driving precipitation of pyrite in the same system. Kind of fun. And then on the right, these are SEM images of two different photosynthetic mats. They're anoxygenic photosynthetic mats, where you have iron sulfide precipitating in the photosynthetic mat. So they're definitely not oxygenic photosynthesizers. So definite potential analogs for the types of microbial metabolisms that could have been happening at 3.5 or earlier, 3.5 billion years ago or earlier. Another benefit is they can be vectors for evolutionary adaptation. So in hydrothermal systems, typically have thermal lakes associated with them. So this is an example of firehole lake area. So we have geysers and hot springs, and then a hot lake behind them. And so this provides an avenue for life to then move into a more quiescent, cooler environment, which then outflows into streams and rivers and the ocean. And so that also provides an avenue for organisms to adapt to those sorts of environments as well. And thermal ground is in contact with hydrothermal systems too. And so this provides a vector for life to adapt to drier and cooler environments. And so this is an image from a paper Trinity I put out looking at hypoliths and how these hypoliths might actually be a proxy for how life first was able to adapt to living on continental surfaces. And of course, this has been wonderfully summed in like there's a paper by Martin van Kranendonk and his co-authors, kind of summing all of these little points that I've just made. And so if you're interested, I highly recommend. It's a very quick read and kind of fun. And of course, have to give a shout out to Chuck Darwin, of course, with his quote about warm little ponds that he wrote in his letter to his friend Joseph Hooker in 1871. And so it's fun to see how the warm little pond idea, or basically a hot spring idea, has come back into vogue now, I think, after in the 70s when deep sea vents and black smokers were first discovered. That kind of took over the conversation of where life could initiate. We finally, I think, come back to thinking again about hot springs as a potential really great place for life to originate. And so I wanted to then move to giving an example of an early potentially hydrothermal system in the rock record. And so I'm going to talk about the 3.48 billion year old Dresser Formation in Western Australia. And so this is, of course, with my collaborators, Martin van Kranendonk, especially Tara Jokic, who did her dissertation work in this system. So shout out to them for allowing me access and including me with that. And so in the Dresser, there have been Tara discovered what she believes, and I believe as well, after seeing them myself with my own eyes. She thinks that she has found fossil hot spring systems, and the evidence is really just astounding how well they're preserved for something that's been around for 3.5 billion years. They've been, for those of you familiar, they've been altered to green schist facies, which has allowed a lot of textural information to still be preserved. So it's relatively high, but not too high in terms of temperature and pressure. But for example, from Tara's work, she's shown, for example, here's pictures of what look very much like what geyserite would look like if it formed around the rim of a hot spring pool, and then all the swirly, chaotic deposits, also very indicative of how hydrothermal systems deposit chaos. Remember that chaos. And so you don't have regular sedimentary events, you don't have regular things happening, you have chaos. And so that's one indicator of hydrothermal systems. And on the left, I have my fingered for scale looking at what would look very much exactly like what stream edge stromatolites that I've studied in Yellowstone look like. And then a very thin microbial mat, which would have been in a fast flowing region, which would be similar to an outflow channel for a hot spring. And so a lot of really, really fascinating and intriguing textural evidence. So we have a pop quiz now, low stakes. So what I want you to do is decide which of these, A or B, so left, A on the left, B on the right, which of these do you think is from the Dresser Formation, that's 3.5 billion years, and which is from modern hot spring in Yellowstone? So give you a second to choose. So lock in your answers. All right. So the answer is A. A is Dresser. On the right is some geyserite that I collected from this hot spring in Yellowstone National Park. And this is a very texturally similar sample from the Dresser Formation we were just talking about. And a lot of this textural information, and so this figure on the right is a sample from Norris Geyser Basin that incorporates a bunch of broken up pieces of hot spring sinter that have accumulated into a lag deposit, and then a similar deposit from the Dresser Formation. And this really blew my mind. So if you I zoomed in on two pieces with SEM imaging, and I was able to differentiate the original sinter from a silica rind that had deposited around it, and found the same texture in the Dresser. And zooming in closer, one for one, this amorphous silica that had formed as a silica sinter, and the same textures, even with the void spaces, preserved in this Dresser Formation example. So just wild that this is preserved this well. And of course, it's intriguing to think about life. We have, of course, n=1, but hopefully, maybe we can break from n=1 to n=2. So I'm going to talk a little bit about some of the active missions on Mars. And specifically, I'm going to talk about the Mars Perseverance rover from Mars 2020 mission. And so for those unfamiliar, this rover was landed in Jezero crater. And so, and here's a fun little GIF of Perseverance rover after having taken a selfie picture of itself and a few cores that are drilled. So on the right is a USGS image, a oblique image looking at some delta deposits that are deposited from a river in the crater, and then there's the rim. And so the thinking is that a lower left, this is an artist's rendition, that Jezero crater was a home to a lake. And so there's flow coming in from the high country, flowing into the lake, and the delta deposit happened here where this is draining and hitting the lake, and then it drained out into the Isidis Basin. And so there's lots of excitement because there's carbonate rocks that are precipitated around the rim. You have this delta deposit, which accumulates a lot of sediments from above. So it's a great gathering point for a lot of different information. And so just for reference of where Perseverance is right now, and you can look it up on the NASA website. So this is as of this morning, Perseverance landing over here, moving around, and now has moved onto the delta and is working its way up. And each of those red spots represents where a core was dropped of a sample for potential sample return, which is hugely important, I think, in terms of thinking and how we can use the information that I've been talking about to interpret once we bring those samples back, if we happen to collect hot spring samples. And you think, well, this is a lake. What does this have to do with hot springs? And so something I wanted to bring your attention to is if you take a step back and look at Jezero crater context. So here's Jezero crater. Here's the catchment area that is estimated to have drained into Jezero crater to deposit in that rim. That's a very large area. And so Jezero crater, which formed about 3.8 to 3.5 billion years ago, is at the edge of the Isidis Planitia, which is the Isidis impact basin, a huge basin that formed about 4 billion years ago, massive. And so with hydrothermal, with these large impactors that generate a lot of heat and actually drive hydrothermal, modeling has shown they can drive hydrothermal processes for millions and millions of years following the impact. And so these this rim, and these are fractures from the rim of the acidus impactor, we fall right into this. So there's potential for old hydrothermal deposits from that impactor. And also we have Syrtis Major, which is a large volcanic province that is active, primarily is active about 3.5 to 3.3 billion years ago. And so this, again, another source of heat. So we have source of sustained heat from volcanism, source of sustained heat from impact occurring in this region. So we have multiple avenues for potential of driving hydrothermal features and hydrothermal processes. And so, maybe some of this was delivered from the catchment area. And of course, as the rover climbs the delta, it will eventually climb up into the rim country. So there's even an opportunity of running into old hydrothermal deposits from the earlier times as well. And so it's very exciting to me to think of, if we are prepared, we might be able to actually collect hot spring deposits and cache them and maybe even bring them back. So hopefully, in terms of take-homes, I've been able to communicate well that these large data sets are really helpful with understanding processes and helping with predicting and interpreting the rock record and early origins of life environments. Terrestrial hot springs can provide an ideal location for initiation and diversification of life. And there's hope that we might even be able to identify and characterize hot springs or past hot spring deposits on Mars. And so with that, thank you for your time, and I'm happy to answer any questions anyone may have. So thank you.
All right. Thank you very much, Jeff, for that amazing talk. So we'll open the floor for questions now, and you can either raise your hand or type your question in the chat. So while people are thinking of some questions, I got a couple for you. And
sure, yeah,
they're really pretty basic. I'm not a geochemist. I'm just still trying to understand the basics of hot springs. So I noticed, for your chloride concentrations that the max was maybe like 100 millimolar or something. And I'm just trying to think of the mechanism. So like you have these subsurface transport mechanisms that are bringing the chloride to the pool. So I would naively think that some of these pools must be hundreds, thousands of years old. Wouldn't you expect just over time you get saturated concentrations of something like chloride?
Well, that's an excellent point. And so with most of these hydrothermal systems, they're not closed basins. They're of course open and exposed. And so most of them typically have outflow channels. That's very, very common. And so there's always going to be input and flushing and outflow. But then also you have rain coming in and washing things away. And so even on these surface, if you have surfaces, so lots of these gases are coming up diffusely in these hydrothermal areas too. So there's no pool. You just have acidic vapor, steam coming up, interacting locally and precipitating salts. But then every thunderstorm that comes through washes away and resets. And so the meteoric input is also a critical component, which I didn't really talk about. So thanks for that question to iterate with that. There's always flushing, there's always stuff pushing through the system as well.
Right. Okay, yeah, that makes sense. And another question related to subsurface transport. Thinking back in prebiotic times, would this be a mechanism for, say, different organics that are being produced atmospherically, just like over a wide region? Maybe like they settle onto dry land, and their concentrations in that particular area maybe not too great, but then could this subsurface transport be a mechanism for collecting all of those organics produced atmospherically and just concentrating them down?
Absolutely. And I would say even surface transport. So if you have dry deposition of organic material falling onto a land surface. Lots of these hot springs tend to be, especially the acidic ones, tend to be depressions. And so you would have, and we see this every time it rains, with the bison having deposited bison poop usually around these. If you get a big like rainstorm or rain event happens, you get washing in of this organic material. And so I think that's really, absolutely, I think you're 100% on that we could have transport of accumulations on even dry surfaces. They're just brought in to the hot spring from just even surface. Yeah, absolutely.
Yeah, and one more follow-up to that. So, like, if these organics would be transported in the subsurface, and they get close to the magma chamber or whatever, and get really heated to a high temperature and under high pressure, do we have a good understanding of what happens to say some mid to small size organics? Would they all kind of get processed and yet again, or would we expect them to just kind of stay as they are?
Yeah, and I'm certainly not an organic geochemist, so I will not speak to as an expert on that. But there's a lot of great information from like petroleum geologists and thinking about this, and people that deal with like very high metamorphic rocks, and thinking in terms of what happens is it gets cooked down to carriage, and so there's a lot of great information about that. I won't speak to it myself, but there's a lot of great information thinking about what happens to those, what could happen to those molecules at those high temperatures and pressures. And of course, it's not good, but
Yeah.
in general.
Okay. Yeah, thank you. So we have a question in the chat from James. So on Mars, where the source of heat may be from impacts, there won't be magmatic sources of different volatiles, anions, cations. Have you thought how that may influence hydrothermal springs generated by impacts?
Great point. Thanks for bringing that up, because I just really glazed over thinking in terms of hydrothermal sources and impacts from impacts, and effectively. And again, I'm not a expert on impact effects, but from what I've read and from what I understand, it's effectively creating it's like creating a magma. And so it has a lot of the same types of effects as if it were a volcanic process, but maybe potentially less in terms of those magmatic gases. And so I think that's a really exciting thing to think about, that I don't know of anyone's really done much work on that. And so it'd be really interesting to try to maybe do some modeling, what exactly would happen, and what would the thermal waters look like. I mean, from what we've learned, I can at least say if we have a starting point chemistry, we can tell you what would happen to it as it reached the surface and where the elements would go. But yeah, it's a really exciting and interesting question, thinking in terms of what would be the differences between hot spring from strictly impact generation versus a magmatic source, volcanic source. So yeah, awesome question, and hopefully someone who's good with modeling can maybe tackle that.
Yeah. All right, we have another question from Suki Smaglik, who asks, has there been any geochemical work of this type that you know of done on shallower non-magmatic hot springs with different non-volcanic lithologies?
Yeah, and my focus has obviously been in Yellowstone and these big hydrothermal systems, and so I don't know of anyone that has compiled a lot of data to try to tease apart what's happening. So I'd say if that's a really exciting avenue that's wide open. So if you're passionate about that, it might be an opportunity to fill in a necessary gap in our knowledge and thinking.
Yeah. All right. And we have another question from Emma Nursazova. Hello from Kathleen's lab, she says. Thanks for the great talk, Jeff. We know that hot spring silica deposits concentrate elements at orders of magnitude higher than what is in the source fluids. How do you think this impacts trying to interpret the fluid vapor regimes from past sinter deposits.
Yeah, and so that's something that I'm very interested in as well. And so I had referenced the paper we had put out here in 2021 a lot with looking at the big picture of geochemistry and characteristics of hot springs. And in that, we also looked at sinters and trying to think of so what does it look like for how is the fidelity of a sinter or silicious silica deposited from these thermal systems that are all supersaturated with silica, depositing silica. How well do they preserve the signal? And so we were thinking in terms of life as a biosignature, and so in terms of these surface samples, and we found that there's kind of a systematic retention of certain elements, but a lot of it is lost from just surface weathering and meteoric water passing through, dissolving and moving things through. And I think specifically to the idea of how well would sinter be, how good would sinter be as a how good is the fidelity of the preservation of that signal? I think that's still pretty open to interpretation. So, and is an open avenue of investigation. So I'd say, hopefully maybe you would be able to help us learn more. Again, it's these things that we're still, I think, really trying to get a good handle on. And of course, there's a lot of great work that's been done by geologists look at ore bodies from hydrothermal systems that we're still working to really do a good job of trying to bridge their knowledge with the knowledge that folks like me are coming at it. So I think, again, a really fascinating, exciting avenue to push forward on.
Yeah, very good. Yeah, I've heard from Martin Van Kranendonk, many times that these hot spring environments, they have these very diverse, geochemically speaking, pools in close proximity, and you have lots of chances for mixing. And when you mix, you can change pH, you can change different concentrations of various things. And yeah, I think that would be beneficial for prebiotic chemistry, generally speaking. The challenge always is, how do you model this type of thing chemically in the lab? That's I think that's always kind of the biggest challenge. That's more of a comment than a question, but I was wondering, maybe you have some thoughts on that. Like, how, as a chemist, would you recommend that we go in and try to reconstruct a sort of artificial hot spring, let's say?
Yeah. And I mean, honestly, just from my time in science, from when I was an undergrad to now, there's been a huge change and shift and blossoming of origins of life work being done. Because when I was a budding young geochemist, there was very little work being done in terms of trying to tease apart origins of life chemistry. It's basically like the Urey Miller experiment and then themes and variations on that. But I think now more and more people are starting to do some really exciting things. Like from the biology side, people are working to reduce organisms to the bare minimum to see like what's the bare minimum it takes to have a viable living organism, right? So that's really exciting to think of what can we strip away, what can we take away. So that gives us thinking in terms of what's necessary. But then from like chemistry perspectives, there's lots of different labs that are starting to do like this, even just little simple experiments of putting lipids into different types of thermal and geochemical environments and what happens with them, right? And so if you start to put lipids into different chemistries, see what they do, and then can you then send them through wet dry cycles? Can you if you add different types of proteins or DNA, do they get incorporated in those lipids? And there's been work done on that as well. And so I think that there's just a lot of really exciting lab chemistry being done of looking at little small parts of origins of life thinking and actually coming up with some answers. And so for me, it's just like, it's super awesome to see that it's really exploding, and a lot of people are starting to push on that and do really interesting experiments in the lab that just weren't around, honestly, 20 years ago, 30 years ago. So
Yeah, yeah, I
kind of
agree.
helps.
I think we're also kind of in the beginning stages of this uh, new field of trying to better understand like potential prebiotic chemistry in hot springs. And yeah, it is really fascinating. Yeah. We have another question from Rebecca Guth-Metzler. Thanks for the talk, Jeff. Thinking about how much of an impact surface hydrothermal systems may have on the environment, especially an early one. How far from a spring could one still find chemical influences of the spring?
So great question. And that kind of gets into the types of hydrothermal systems. So I didn't really get into it too much, but typically you have, for example, in Yellowstone, if anyone's been there, you probably have noticed that there's a lot of, you get the places where there's acidic stuff and places where there just isn't. And so you have hydrothermal systems that are either mostly this minimum phase separation types of hot spring. So like the grand prismatic type things that are Old Faithful. And so that's where you see a lot of very similar types of chemistry happening. And those tend to be more localized. And so you don't get as much impact moving away. But in the subsurface, of course, that the heat is impacting a fairly large area in the subsurface. And so on the surface, you may only see a relatively small area around the pool, and then the outflow channel where you can see photosynthetic mats. So that clear indicator of where the thermal systems are working on the surface. But in the subsurface, it can be greater than what you would see, especially as different plumbing opens and closes in the subsurface as a hot spring can evolve. But then if you get into the more where you have subsurface boiling, that's where it really cooks things and messes with things. So you have that phase separation, you get lots of acidic fluids being generated. And so you'll see, you can see them on Google Earth. You can look at them and measure them. Sorry. So you can have, half to full square kilometer or more of surface expression of hot springs and completely hydrothermally altered rocks and within that hydrothermal area. And so the impact can be, the impact from one hot spring may be on the orders of meters, but in terms of a hydrothermal area, they can be kilometers. So it'd be quite large. And of course, on early Earth, we didn't have that many kilometers of surface area to work with at all. And so, that could have been actually quite a bit of the land surface real estate that we had available. So hopefully that
Cool.
helps kind of give a feel for that impact.
Yeah, she says, neat. All right. Well, seems like if there are no further questions, we'll go ahead and wrap it up right there. And just want to say thanks again, Jeff, for the great talk. And yeah, we'll see you back again in 3 weeks' time.
And thank you again, everyone, for your time. I really appreciate it.
Yeah, thank you.